Hello YouTube. This one's this one's gonna be kind of a lot. Honestly, if you're okay with just having the kinematic equations and not knowing where they come from, um, there's a little bit at the end of this video that's still gonna be really useful. And personally, I do think it's actually pretty useful and helpful, especially for a couple of the AP questions, to know where the kinematic equations come from. But today's going to be pretty heavy on the math, and there's not really going to be a bunch of punches pulled on it because we're basically doing calculus without doing the calculus. So, if you skip ahead to the point where you don't see a piece of paper anymore and then go a little bit before that, I'll have all the kinematic equations up on the screen, and I'll talk about and go through how... Oh no, that's the next one. So yeah, we're just going to do the derivation for this one. So if you want to skip ahead to the next one, that's honestly totally fine. But this is where everything we're going to be using for this unit comes from. So if you like knowing why things are true and just instead of just sort of assuming that the stuff I tell you is true, today is really important. All right. Ideally, we're going to start the process of describing the motion of an object that's having constant acceleration, and that last bit's really important. We've done constant velocity, but we haven't talked about how it moves if it's accelerating. We talked about what happens when it's not accelerating in the first unit. In the second unit, we talked about why things accelerate, which would be forces. And in this unit, we're going to be talking about, once you know how much it's accelerating, why is that useful and what can we do with that? So ideally for today, if you can just follow along with the derivation, you are well ahead of where you need to be. You will probably never have to do this, but you will have to use a few of the ideas from it. So still useful. That's enough stalling. Let's derive some stuff. So what I want to do is say, okay, let's think about an object that's going from point A to point B. And let's actually be a little bit less specific than that. Let's say it's going from point A to some arbitrary point X. And what I want to be able to do is, at any point in time along the way, I want to be able to figure out how far it's gone and in what direction, which would be our displacement, measured in units of meters. I would like to be able to figure out how fast it's going at any given point in time, which is x. Vx. The only reason the x is there is because it's there on the AP exam sheet. Honestly, there shouldn't really be a subscript there. This matters when we get to two-dimensional motion, because having an x version and a y version, just like how having subscripts for x and y for forces was useful, will be useful for this stuff as well. And I want to be able to figure that out for any given time. And for a known acceleration. So let's say we have an acceleration and we know that it's constant. And that is the only assumption we're going to make. And we're also going to say that it would have started at a given velocity. So Vx naught is the initial velocity of the object. Delta x is dependent on how long you wait. Vx is dependent on how long you wait, because it'll be changing its velocity throughout. The time will change throughout. The acceleration will be the same throughout the whole thing, and the initial velocity will be the same throughout the whole thing, unless you start thinking about it differently, as like starting from a different point in time. What I want to do is find a set of equations that relates all three of these things, relates these things as much as possible. We'll then have a secondary objective to get the next two equations, but the first two equations are just coming from a desire of, I know that this thing is going with a constant acceleration. What does that tell me? And to do it, we're going to do a geometric derivation. If you know calculus, it's literally that velocity is the integral of acceleration. So you just take an integral once with acceleration equals some constant value a, and that gives you the velocity equation. Don't forget to add your initial velocity. Do it again. That gives you your displacement equation. Don't forget to add your initial position. That's it. But we don't know calculus. So we're going to do it graphically by using some of the stuff from Unit 1, which hopefully you still remember. So we have a constant acceleration at a value of a sub x. And we want to go to some arbitrary time t. So after t amount of time, we want to figure out what this graph can tell us. Well, if we have an acceleration graph, the area of that acceleration graph will give us the change in the velocity. So if I go from here to here, this area is going to have a base of t and a height of ax. So my area here is going to equal the acceleration times the time. And what that will also equal is the amount that my velocity has gone up or down by. One more step and we've pretty much got the equation. Change always means final minus initial, which in this case is Vx minus Vx naught. So I'm going to take this and rearrange it so that it's a variable, the current velocity, in terms of the time and a bunch of things that we hopefully know at the beginning of the problem. So doing that out, we'll get ax times t equals Vx minus Vx naught. I want to try to solve for Vx, so I just have to add Vx naught to both sides. Again, our goal here is to just get a set of equations that tells us what's going on with this stuff. So we've got Vx is equal to Vx naught plus Ax times t. And sometimes I'll flip the order on those two. Doesn't really matter too much. I think this is the order it's on the AP exam sheet or equation sheet, which is why I write it like this, but you could flip it and it'd be fine. So what this is telling us, and I'm going to call this equation 1. What this is telling us is that if we want to figure out how fast we're going at any given point in time, all we have to do is take what we started with and add the amount we change by, which is our acceleration times our time, which hopefully actually makes a decent chunk of sense. I can use this to make a velocity graph. Why would I want to make a velocity graph? Well, we know how to turn velocity graphs into position graphs. The geometry for this will work whether or not it's positive or negative and whether or not it crosses the axis. I'm going to make it so it's a little bit easier and doesn't do either of those things. Now my slope here is equal to ax. My x-axis is my time. We talked a little bit about linearizing, hopefully by now, in Unit 0. This is kind of like a linearization problem. I know that my slope is ax. So if we're looking at the equation form, we have y equals mx plus b, where this is our b, this is our m, this is our x. So our x-axis is time, so that's why that's x. Our slope is the acceleration, because that's the amount that we go up by each second. Our initial velocity is our y-intercept, and whatever our current velocity is will be our y value on the graph. Now what I can do here is once again start thinking about the area and the shape, because the area of a velocity graph gives us position. And so if we want to, or displacement. And so if we want to find displacement, this is a great way to do it. If I go to this arbitrary time t, then I'll have a rectangle and a triangle. Now the base of the rectangle and the base of the triangle will both be t. The height of my rectangle will be from the beginning of the triangle. Well, the beginning of the triangle is the y-intercept, and the y-intercept is Vx naught. So my height here is Vx naught. So if I want the area of the rectangle, that'll equal Vx naught times t. If I want the area of this, I'm going to have to try a little bit harder. Now the base is t. That part's fine. The height's a little weird. The height will be the value of our current velocity after a given amount of time. Well, the value of our current velocity after a given amount of time is this, right? So Vx naught, but I've already gotten rid of Vx naught by going up this much. So then the question is, well, what's left over? Ax times t. Hopefully that makes some level of sense because the slope is ax, and if we take the slope and we multiply it by the amount of time, it gives us the rise. Rise over run equals slope, so slope times run equals rise. So my rise here is ax times t. But this is a triangle. So to get the area of my triangle, that'll be 1/2 base height, or 1/2 times the time times ax times t, which will give us 1/2 ax t squared. What we can then do is take there's my pen. I feel like there's another one that, yeah, right here. What we can do is we can take those two areas and put them together, and that will give us our displacement because the area on a velocity graph gives us displacement. So that'll be Vx naught times t plus 1/2 ax t squared. This is our second equation. So those are our two main kinematics equations, and with those, in theory, we can figure everything out. What I want to do from there is start talking about how these equations get used, and then talk about why it would be useful to have two more equations so you can save yourself a lot of algebra in the future. One of those other two equations will wind up on the equation sheet. One of them will not. We will derive both of them. So, quick thing about these equations. If you look at this overall, there are 5 total variables. But if you look at each of these equations, this one's got 4 variables. This one also has 4 variables. So in particular, this first one does not have displacement. So if you are asked for a problem that does not include displacement, you're not trying to find it and you're not given it, that first equation is really nice because it means you can only have to use one equation. If we come over here, this one's got no Vx. So if you don't know the final velocity and you're not asked about the final velocity and you don't care about the final velocity, well, this is it. So what we're going to do is figure out an equation that works without time, because that's a situation that comes up fairly often. And then we're going to figure out an equation that works without acceleration. We're not going to worry about the one without final velocity, because to get the one without final velocity, you can think of this one, but backwards. And it will still work. Oops. So basically, you would make time negative when you were plugging in, and it would be true still, but with the final velocity instead of the initial. And I'm fairly certain that'll work. So what we're going to do in order to get our other equations is take these two equations and plug them into each other for solved versions in order to get new equations. This is the part that's probably really going to lose people historically. I do still think it's useful. I think it's useful for you to see the algebra. I will not necessarily expect you to repeat this algebra. My goal, as of right now, is to, 1, get rid of time, and then 2, make it pretty. This second step is going to involve some kind of fancy stuff. The first step will not. Yep, that's the plan. Okay, so what I'm going to do is take the easier equation, equation 1, and solve for t. If I do that, I've got Vx equals Vx naught plus Ax times t. I need to get t alone, so I'm going to need to bring everything without a t over to the left. So we'll get Vx minus Vx naught equals Ax times t. We want t alone, so we'll divide each side by Ax. Divide each side by Ax. At this point, we've got a solved equation for t. Vx minus Vx naught over Ax equals t. What I can then do is take this and plug it into equation 2. If I do that, what I'll be left with is an equation that does not have t in it because I will have turned t into something that uses the other two variables. So what that'll look like is delta x equals Vx naught, and then I need to include my thing for t, which is Vx minus Vx naught divided by Ax. Over here, we've got plus 1/2 Ax times t, all of which is going to be squared. So that's Vx minus Vx naught divided by Ax, again, all of which is squared. I'm going to absolutely run out of room, so I'm going to just rewrite this on the back. So we've got that delta x equals Vx naught times Vx minus Vx naught over Ax. We've got plus 1/2 Ax times Vx minus Vx naught over Ax quantity squared. Great. Next step here is going to be to do out the squared. At this point, we are done. Technically, this equation works, but unless you want to write this equation every time you have to solve a problem without time, we're going to make it pretty. So I'm going to distribute the squared. In order to do that, I'll get Vx minus Vx naught squared, which, let me get everything else settled up first. I'm actually going to distribute this Vx naught while I'm at it. That'll give us Vx times Vx naught minus Vx naught squared. That's being divided by Ax. Plus 1/2 Ax times Vx minus Vx naught squared. That's going to be Vx squared, then Vx times negative Vx naught, then Vx naught times negative Vx naught times Vx, then Vx naught squared. And that's all going to be divided by Ax squared because that's also getting squared. At this point, I'm going to do something to simplify a little bit. Those two cancel because Ax times Ax is Ax squared is Ax times Ax. So one of the Ax's on top is going to cancel with one of the Ax's on bottom. At this point, to get rid of the denominators on all of this, I'm going to multiply each side, all of it, by 2 times Ax. That cancels this Ax and this Ax with this one. The 2 distributes here and gets rid of the half. The 2 also distributes here. So pausing for a sec to make sure you got all your stuff written down. Great. From there, we've got 2Ax delta x is equal to 2 Vx naught Vx minus Vx naught squared times 2. Have to remember to distribute, almost didn't. Plus Vx squared minus Vx naught Yes, okay, good. Sorry, I was just double checking that I don't have things mixed up. There's 2 of these, so they're going to combine to 2 Vx naught Vx, which is combining like terms, plus Vx naught squared. We can also combine like terms here with these 2. And we can combine like terms here with these 2. We have positive and negative, so those 2 cancel. And what we're left with is 2ax delta x equals Vx squared minus Vx naught squared, because negative 2 plus 1 gives us negative 1. One last step. Add Vx naught squared to both sides. So our final equation, just for the sake of getting it a little bit prettier, is this. And this is basically the equation you'll find on your equation sheet. They don't write delta x, they write x minus x naught. I think that that's kind of one extra step, and normally you can just use the displacement, so I left it like that. So this is our equation without t. If you don't want to use time, this is a great equation to use. The last thing I want to do at this point is get rid of acceleration. So to get rid of acceleration, I'm going to take equation 1, solve equation 1 for acceleration, and then I could plug it into either of the other 2. I think it'll be easier to do it in this one because we're not going to have to wind up worrying about anything with a squared that way, and that seems a bit nicer. Or at least not time squared. So next step is to solve equation 1, which was Vx equals Vx naught plus Ax times t for the acceleration. So to do that, we need to again subtract off Vx naught, subtract off Vx naught. This is going to look very similar to last time we solved this one for something. But now instead of dividing by Ax, we're going to divide by t. So we've now got a way to represent acceleration in terms of the other stuff so that we can get rid of acceleration if we plug it into one of the other equations. I'm going to take this and plug it into equation 3. When I do that, I'll get Vx equals Vx naught squared plus 2 times this thing times our displacement. At this point, I want to make this pretty. So to make it pretty, we're going to solve for delta x and simplify. This part is probably going to lose some people because it's going to involve some algebra identities. Sorry in advance. I need to move everything without a delta x over to the other side. So I'm going to subtract off Vx naught squared from both sides. So we'll have Vx squared minus Vx naught squared equals 2 times Vx minus Vx naught divided by time times delta x. 2 more steps. One of them is to just get delta x alone, and then the last one is to simplify. I need to multiply each side by time to cancel out the time. I need to divide each side by 2 to cancel out the 2. I need to divide each side by Vx minus Vx naught to get rid of the Vx minus Vx naught. So So I'm going to do this over here as well. Times time, divide by 2, divide by Vx minus Vx naught. And I'm going to swap the order around a little bit just to make it prettier for the final result. And that gives us Vx squared minus Vx naught squared divided by Vx minus Vx naught times 2, all of which is times t. I want to do one more thing, which is to use an identity from algebra, which is that a squared minus b squared is equal to a plus b. In this case, a is Vx and b is Vx naught, times a minus b. These are the same thing. If you want to double check, you can remultiply. We'll get Vx squared, negative Vx naught Vx, positive Vx naught Vx, which cancels with the negative one, and Vx naught times negative Vx naught. So Vx naught squared, which is the same as this. The reason I'm doing that is that these two cancel. So what we're left with is the equation that's not on the AP Physics exam equation sheet, which personally I think is a way better equation because it actually means something. If you look at this part right here, so this is our equation before I get into that. It's not on the equation sheet and it's got no acceleration. Conceptually, this part right here is your average velocity. If you have a constant acceleration, you can take your initial velocity, your final velocity, and get the midpoint of those two because it's a straight line, and that will give you your average. If you take your average velocity and you multiply it by time, it gives you displacement. So this is literally just our average velocity equation, expanded out a little bit. Took a few steps to prove it, but we did it. So those four are your four equations. Going back through them again, hopefully without smacking the microphone as much as I just did. We've got Vx equals Vx naught plus axt. This is the one that's really good if you don't have displacement. We have displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. I don't know why I swapped to using the concepts instead of the variables, but here we are. That one's really great if you don't have final velocity. We've got final velocity squared is equal to initial velocity squared plus 2a times delta x, or displacement. And we've got our last one, which is that our displacement is equal to the final velocity plus the initial, divided by 2, which is average, times time. So, a little bit intense on the math, but that's the derivation of all the equations. Feel free to leave any questions in the comments, and thanks for watching. Goodbye YouTube, that's the one.